Hello. In this video, we're going to talk about correlation, in particular the Pearson R Statistic. We're going to look at how correlation is a measure of how two numbers are related and then how that applies to our studies in education. First of all, it makes most sense to go ahead and give credit where credit is due. The Pearson R Statistic, the one that we're going to be talking about so much in this video, was developed by Karl Pearson. Karl Pearson is a renowned statistician. In fact, he is a person that lots of people give credit to for inventing the whole study of modern statistics. So Karl Pearson is the one who developed this idea, and so it bears his name. It's called the Pearson R Statistic. It's a measure of correlation, which is to say how two different sets of numbers are related to each other. So let's jump right in and start talking about the Pearson R Statistic. This particular statistic is a number or a metric that tells us two different things. It tells us the strength of relationship between two sets of numbers and also the direction of the relationship. You'll notice also on the little side note there that it's on a scale. It's on a scale all the way from -1 up to a +1. When we talk about the direction of the relationship, what we're talking about is the kind of relationship that's going on between the sets of numbers. And there's two different kinds. One is a positive relationship. I'll keep it really simple. A positive relationship happens when between two sets of numbers when as one number goes up, the other number goes up, the corresponding number in the other set of data. Or you could think of it this way, as one number goes down, the other number goes down. I have the arrows there to represent kind of visually in that way with symbols. As one goes up, the other goes up, or as one goes down, the other goes down. Also, if you're a kinesthetic learner, you may want to think about it with the thumbs up. As one number goes up, the other goes up, or as one number goes down, the other goes down. So we might be saying, for example here, as one's confidence level on a particular test goes up, generally their score on that same test is going to go up. But as their confidence level goes down, then odds are their score on that test is going to go down. So if that kind of relationship is happening between two sets of numbers or two pieces of data, we would call that a positive relationship. A negative relationship then is, I guess you would think of it, just the opposite. As one number goes up, the other number goes down. Or as one number goes down, the other number goes up. There's two different ways to kind of look at it. There's the arrows there to represent symbolically what I'm talking about, or as one number goes up, meaning thumbs up, the other one would be like thumbs down, the other goes down. An example of a negative relationship would be something like maybe the number of incomplete assignments in a class and then the overall grade in that class. As the number of incomplete assignments goes up, the overall grade for that course generally goes down. So there would be a negative relationship between those two sets of data. Just to draw a connection to your algebra days, maybe think about pre-algebra and Algebra 1 class. And we did talk about relationships back in those days, and we talked about these same two kinds of relationships, but we gave them different names. The positive relationship is generally called in algebra a direct relationship, and the negative relationship is often referred to as an inverse relationship. So that might help too to draw the connection to your pre-algebra or algebra days in school. So let's think more about this scale of 0 in the middle all the way up to +1 down to -1, the scale that a Pearson R value could take. This is going to help us determine not only the direction, because there's positive numbers between 0 and 1 and negative numbers between 0 and -1, but it also helps us determine the strength of the relationship. Let's start at the very middle where the 0 is. If the Pearson R value is calculated to be 0, then what we would determine is there's no relationship between the two sets of data at all. As one number goes up, the other number may go up or down, or vice versa. There's just absolutely no connection whatsoever. When that calculated out, for example, in SPSS, gives us a Pearson R value of 0, we would say there's no relationship. Now let's work our way up into the positive territory closer to 1. If we get a small positive value, like maybe a 0.2 or a 0.3, we would describe that as a weak positive relationship. So it's still positive in the sense of both numbers going up at the same time or both numbers going down at the same time, but it's a weak relationship because it's closer to the 0. As we work our way up a little bit further, maybe somewhere there like 0.6 on the scale, that would be a moderate positive relationship. And then closer yet to the 1 would be a strong relationship, an extremely strong relationship at something like maybe a 0.9 as the Pearson R. If we work our way down into the negative territory, a weak negative relationship would be right there on the scale, maybe like a negative 0.2 or negative 0.3. A negative 0.6 would be a negative relationship because it's between 0 and negative 1, but it's moderate. It's a little closer to the negative 1 and it's further away from the 0. And finally, a strong negative relationship would fall on the scale somewhere like right there, maybe like a negative 0.9. As you start to think through all this about how these Pearson R values relate to each other, it's interesting to consider it from this perspective. A Pearson R value of 0.9 and a Pearson R value of negative 0.9 actually have the very same strength. So in terms of how far they are from 0, they have the very same distance, the 0.9 away. But they are totally different relationships or directions. So a 0.9, of course, is a strong positive. A negative 0.9 is a strong negative. Another thing about this, as you're starting to piece it all together and it helps make sense, is what if you were comparing something like a Pearson R value of 0.4 to a Pearson R value of negative 0.6? Well, the 0.4 is obviously positive. We describe that as moderate. The negative 0.6 is obviously negative. But the negative 0.6 indicates a stronger relationship between the sets of data because it's further down away from 0. It's a greater distance away from 0 than the 0.4 example. And so don't think about these in terms of the way you normally interpret numbers. All the time 0.4 would be greater than negative 0.6, right, on a typical number line. But in terms of a Pearson R, we're thinking about the strength of the relationship being represented by how far it is away from 0. And so a negative 0.6 is actually stronger than a positive 0.4. Another way of thinking about this, I'm going to put my arrow right there in the middle where the no relationship is. That's a Pearson R of 0. As that arrow climbs up closer and closer to 1, the relationship is getting stronger and stronger and stronger, and that's on the positive side. If we start back at 0 but work our way down, it's getting stronger and stronger and stronger, but this time on the negative side, talking about a negative relationship. Just to illustrate this in an alternate way, this might be a graphic that would even help further solidify what we're talking about. All of the values between 0 and 1 are positive and represent a positive relationship. So any Pearson R value that falls in there between 0 and 1 would be positive. Anything between 0 and negative 1 obviously then would be negative as it falls between the 0 and negative 1 on the scale. From 0 to 1 you have an increasing strength of the relationship, and if you go from 0 down to negative 1, as you move that direction you have increasing strength as well as you get closer to the extremes, negative 1 to 1. A couple of other side notes about Pearson R. First of all, it always falls between negative 1 and 1. There are no exceptions. And so if someone reports to you a really strong relationship because they found a Pearson R of 1.75, well, they totally performed the calculations incorrectly or they don't know what they're talking about. Pearson R only goes to 1 and only goes down to negative 1. There are no exceptions to that. The other side note is that a Pearson R value of positive 1 would be considered a perfect relationship. Also, a Pearson R value of negative 1 would be a perfect relationship. That relationship so tight that it's exactly perfect in step. As one number goes up, the other numbers consistently go up in the same pattern. It's very, very rare, particularly in the social sciences like education, to analyze two sets of data and find a perfect relationship. In fact, relationships that you might think would be perfect in reality are not quite a Pearson R value of 1 or negative 1. Let me give you an example. What if I ask you to give me your year of birth, so the year in which you're born, and then also tell me how old you are? And then we went out and did that for a group of maybe 100 people. So we have 100 subjects in this little quick study. We're asking them just two questions. Tell me the year in which you're born, and tell me then how old you are. Well, are those two numbers related? Of course they are. How old you are is totally based on the year that you were born. Now, is that a positive relationship or a negative relationship? So think about that one. As the year that you're born goes up, say from 1970 to 1975 to 1980 to 1985, your age goes down, right? And so as the year you're born goes up, your age goes down. Conversely, as the year you're born goes down, like from 1980 to 1975 to 1970 to 1960 to 1950 to 1940, your age goes up. So the relationship is one that would be negative. But is it perfect? Is it exactly true all the time that those would be a perfect relationship? And while it seems like maybe yes, the reality is not quite. Because think about it. At any given point in time for that year, not all people have yet had their birthday, right? And so let's just say, for example, I'm shooting this video in the middle of the year, so it's June right now. In June, if all birthdays are equally distributed across the year, then only half of the people have had their birthdays. The other half of the people have yet to have their birthday because it falls later in the year. So let's just pick a number, let's say 1990. So in 1990, right now as I'm recording this video, I hate to date it, but it's 2014. And so in 1990, all people who were born then, now in 2014, they're not all 24 years old, right? Some of them have yet to have their birthday, which means at this point in time, they're still 23 years old. And so there's not a perfect relationship where you can always say 1990 is related to an age of 24. Sometimes it would be 23. Think through that a little further. What if we were shooting this video in December? It'd be a tighter relationship, right? Because almost everyone would have had their birthday. And I guess conceivably if we were shooting the video on December 31st of 2014, then you could say it would be a perfect relationship. But it's very rare in the social sciences to get that kind of strength of relationship from a Pearson R value. Let's take a look at some examples and visually show you. What I'm going to point out here are some scatter plots. Scatter plots are simple diagrams where we plot data on an X and Y axis, and I'm going to use some examples that were going to seem real logical to you. The first one here is comparing the number of minutes studying for a test and then the test grade. And so as we're studying or comparing those two, think about what kind of relationship that would be. Would it be positive or negative? Well, generally speaking, as the number of minutes goes up, the test grade would go up, right? So as I put in some sample data now and plot some ordered pairs or some points on my graph, you can tell as one number goes up, the number of minutes studied, the test grade does indeed go up. Well, I've calculated the Pearson R there because I want you to start to see not only is it going to be positive or negative, but also what kind of strength is it likely going to have. Remember from algebra, back when you're graphing lines like linear equations, if something slopes to the right, up and to the right, that's considered a positive slope. And that's going to be the same kind of relationship here, positive, you can visually tell from the pictures because the blue dots, those data points, are moving up and to the right. If they were moving the opposite direction, like if it was moving downward, the slope was the opposite way, then that would be a negative. We'll see some pictures of that in just a moment. So here I've calculated the Pearson R, and the Pearson R value is 0.97, so extremely strong relationship, positive, between the number of minutes studied and the test grade. I also want you to see this though, already thinking about the idea of how could we draw a single line that would connect all the dots. A single line might look like the red line right there. Even some people call correlation linear correlation. So thinking about how it all relates to that line. And you can tell my blue dots are all pretty tightly clustered around the blue line, the red line rather, which means that we're going to have a very strong relationship. 0.9 indicates that, and it is of course positive. All right, let's take another example. In this case, we're looking at an aptitude score. So that would be like some kind of test where we measure students' maybe potential, and then we're going to see how that relates to a set of test scores. So what would you think? Positive or negative relationship? As one's aptitude goes up, would you think their test scores would go up or down? Well, of course, it's logical. It's going to go up. In my data set here, you can tell that as the blue dots, they kind of form a line. It goes up and to the right, so that represents positive, but it's not quite as tight as the example I showed just a moment ago. In fact, the correlation here is only a 0.71. Still, by the way, very strong for education examples, but not nearly as strong as the 0.97. If we were to draw a line to represent that, you can see how I have more blue dots scattered away from the red line. They're not quite as tight as lined up as they were in my other example. That's what you would expect to see on a scatter plot if the correlation was a little lower. All right, let's take this example. Still looking at test scores on my y-axis. Now I'm going to plot that against students' height, their height in inches. So kind of process that example for just a moment. Think about it. Does it make sense? What's going to happen when you compare a student's height to their score on a particular test? Well, you can probably imagine we're going to get no relationship at all. There's no connection between how tall students are and what they're scoring on a test. And so you would expect to see, it almost looks like kind of a shotgun approach, right? There's just this scattering, all the blue dots are all over the place. In fact, when I ask for the line that best fits all that data, I get this red line here. It's neither positive nor negative. It's not sloping one way or the other. And the Pearson R value is indeed 0, which represents no relationship at all between those two sets of data. All right, now let's start looking at some other examples that are going to indicate a different type of relationship. Now I'm talking about, still again, the test grade, but this time compared to a student's anxiety level. So maybe like a test anxiety, a condition, if we were able to measure that and put it on a scale. If the anxiety level goes up, then likely the test score is going to go down, of course. And so here's what the data looks like. In fact, you can now tell this data is going down as you read it from left to right. If you think about it in terms of a line, it's going to slope or slant the other direction, the other way. When I calculated the Pearson R value for these data points, I got a Pearson R value of negative 0.63. It's pretty strong, the 0.63, and it is indeed negative because as one number goes up, the other goes down. Here's the line that is drawn to best represent the data. I have a few points that are not quite right there on the line, which is why that value is where it is. It's moderately strong, but not an extremely strong value like we saw in some other examples. All right, one more example. This looks at the test score and the number of days absent. In education, we strongly feel like being absent from school makes a big impact on your grade, right? You can't teach students if they're not there. And so we're used to thinking of this in terms of a negative relationship. As the number of days goes up, the number of days absent goes up, then the overall test score goes down. I'm going to show you this in reverse. Now I'm showing you the Pearson R, and I would like for you to imagine what do you think the blue dots are going to look like. So here's the Pearson R that's calculated for the data set, although you're not seeing the scatter plot yet. It's negative 0.95. So in your mind, take just a moment and get a picture. What do you think the blue dots are going to look like when we reveal the scatter plot? So there you go. Is that kind of what you were thinking? If you were able to draw a line, it would pretty well have all of those dots lining up really close to the line because it's such a strong relationship. And the line does indeed slant downward like that because it's a negative relationship. It's the opposite kind of slope or slant than we saw in our positive Pearson R values. So that's a sense about how Pearson R works, and hopefully if you're seeing this for the first time, it's starting to sink in. The Pearson R tells me two things. It tells me the type of relationship, we might say it as direction, whether it's positive or negative, and also the strength of the relationship. And it's visually can be represented on a scatter plot, especially helpful to have that line drawn in as well. I want to share a few final thoughts about correlation. There's 4 points here, and just kind of even further your understanding of how the Pearson R value works. The first is that correlation does not indicate causation. So root words there, correlate and cause. Because two numbers are correlated does not mean that one causes the other. And we have to be very guarded about making that kind of interpretation. Oftentimes people see that two numbers are correlated and they naturally then assume that one's causing the other to happen. And that is not necessarily the case. I'll give you an example. I lived in Memphis for a while, and now I'm in Jackson here at the Union campus. And in Memphis, even though I'm in Jackson, I still watch the Memphis News and read the Memphis newspaper and all that kind of stuff. And it's really sad in the summertime because when the city of Memphis opens all their pools just the community city pools, there's oftentimes reports of different incidences that they have. Occasionally it is near drowning incidences, and other times, sadly, it's drowning incidences. But if someone were to actually collect some data about that and begin to analyze how that number of incidences at the pool is related, you would probably find it's related to, say for example, the high temperature of the day. So imagine a scatter plot that shows the high temperature of the day and then whatever the number of incidences across all the city pools. You would probably find that would be a positive relationship, and who knows, maybe even a strong one. As the temperature goes up, the number of incidents goes up as well. Well, that's not in any way to indicate that the high temperature of the day, as it gets hotter, the day gets hotter and hotter, that's causing there to be incidents at the pool. So just because they're related does not mean they're causing one the other. You can already start thinking through that. Obviously, as the temperature goes up, more people come to the pool, which then likely increases the rate of having incidents. And so what's going on there is the temperature is not causing that, but it is indeed related or correlated to it. So correlation, just because it's correlated, does not mean causation. The second one, a little harder to understand, is that the size of the correlation is a function of the variability of the raw data. And so what we're trying to say here is if the raw data is not varied very much, in other words, it's not very scattered, instead it's more tightly clustered around the mean, it's difficult to get a really strong correlation with sets of data like that. It's easier to find higher correlation values when the original data set is already pretty scattered as it stands. Let me give you this example and see if this makes sense to you. Let's say, for example, that you were going to put together an intramural basketball team at a local college somewhere. Here's a shot from inside Union's gym. And so there's maybe 100 students who come out for intramurals, and you get to go through and pick your team and put together what you hope is going to be the winning intramural team of the season. As you look across those 100 students lined up against the wall of the gymnasium, let's say, for example, that there's no official tryouts. So they're not going to go through any skills or practice or anything like that. You just have to look at them and pick. Which 5 people would you pick to be your starting lineup? Well, most people say, I'm going to pick the 5 tallest people that I can find. And so I'm going to go through and scan them all as they're stand up against the back wall, and I'll pick the 5 tallest. The idea being there's a strong relationship between the height of a person and their ability to play basketball, right? Taller people oftentimes do better in basketball, especially when you think about spread out over the general population. And so if I can't watch them try out, I'm going to make the assumption that I want the tallest people. That's going to make for the best basketball team. However, think about now doing that very same thing with an NBA team. So here's a shot of my beloved Memphis Grizzlies. So I've got a few of them there walking off the court. What if you had NBA players lined up across the back wall in the gym and you had to pick? Would the height of the player necessarily be related that strongly to their overall ability? Well, not really. I mean, by the time you get to the NBA, everyone has really high basketball ability and incredible skills. There's very little variance among the abilities or competencies of NBA players. And so the height is not as strongly related to their ability to play ball because their ability to play ball is all consistently at a very high level. So what was pretty good relationship and might have a strong Pearson R when thinking about it among the general population, then when the variability shrinks down to where there's almost no variance among the NBA players' basketball skills, then there would be no correlation between height or ability. So think through that, see if that makes sense to you. The same thing would happen in a school setting. If you took a group of students that were just, regularly assigned to a class of wide variety of academic abilities, and then you took a group of students that were honor students or maybe even students in a gifted program. Since there's very little variance in students in a gifted program, their academic ability, it would be hard to find some Pearson R's relationships from their academic ability and maybe their grades or their scores on tests. When there's not very much variability, it's very difficult to find a correlation that's high. All right, the third one says that Pearson R should not be interpreted in terms of a percent of a perfect correlation. So we're talking a lot with decimals here. You've heard me use a lot of examples with decimals, and sometimes people interpret that in their brain as just another way of having a percentage. And so I want to reiterate then that a Pearson R value, for example, of 0.75, that does not mean it's 75% of a perfect correlation. So a Pearson R value of negative 0.2 doesn't mean it's 20% of a perfect correlation. So it's not thought of in terms of percentages. Don't convert those decimals into percents. Leave them as they are, as decimals, and don't even think of them as percentages of perfect correlations. And finally, here's the fourth and final point. Be cautious about interpreting correlation in an absolute sense. What we mean here is correlation is always context specific. And so what might be a really good correlation in one setting may turn out to be really not all that special in another setting, even though it's the exact same number. I'll give you an example related to college admissions. We have pretty well across the country two major college admissions tests. We've got the ACT and also the SAT. And when studies have been conducted using those test scores, really pretty well either one, the ACT or SAT, we find that the college readiness assessment, so the score on that test, is correlated to the GPA that a student earns in college. And so you're happy to see that, right? So they are at least related. Think about it, would you be positively related or negative related? Of course, that would be positive, right? As one's scores go up on one of these college admissions tests, then their GPAs in college are likely to go up as well. But the Pearson R value, when calculated in different studies that have been conducted, it's only about like a 0.3, maybe at best a 0.35. And so you think of that on that scale, a 0.3 or 0.35 is really not very strong at all. That would be just maybe slightly better than what you might describe as weak, and I don't know, hardly even moderate. So a 0.3 or 0.35 is not a strong relationship at all. And yet, in our entire higher education system, we continue to rely almost exclusively on these test scores to determine college admissions and scholarships. And so we treat it like it's a lot higher than what it is. Part of the reason for that is we just simply haven't come up with a better measure of predicting one's college GPA based on some kind of previous test that they would have taken, like these college admissions tests. And so the 0.3, while it doesn't seem like it's very strong, is the best we've got. And so we continue to use it. So don't think about these relationships always in isolation. It kind of depends on what's their context about how meaningful the Pearson R is. In the world of college admissions, a 0.3 as a correlation is pretty strong because that's the strongest related data set that we have in order to know in advance what a student's college GPA might look like. So that brings us to the end of the video. Hopefully that helps you with understanding correlation and specifically that Pearson R value, that statistic, which we're going to often use as the measurement of how two data sets are related to each other.